we were finding volumes, and we were using the disk method. So we had rotated a region. And in here, when we say region, we're generally thinking some shape in two-dimensional space. So a region, a shape in two-dimensional space, and then we're going to rotate it around an axis. And then we had our basic principle that if we find a cross-sectional area function, we integrate the area across the domain and we'll get the volume. So we could integrate across a domain that's in the x-axis or a domain that's in the y-axis. If we are rotating around the x-axis, we're going to be choosing a vertical integration element. So if that's rotating around the x-axis, we're going to choose a vertical integration element. If we had a region that was better suited to a horizontal axis, we might be rotating around the y-axis. So we've had two different directions to rotate so far. Now, we can generalize the disk method to this method that we're going to call the washer method. With the disk method, every cross-section was a disk. Well, the only way we're generating a disk is if our region is touching one of the axes. So when we look at our last example that we did, last examples we did, when we rotate this around the x-axis, it's the border, the boundary there is touching the x-axis, so there's no hole. It's wrapping tight around the x-axis, so the cross-sections will be disks. Whereas here, when we take a look at this example right here, this, when it rotates around the x-axis, there's going to be a little gap there. And when we look at cross-sections, we'll no longer have a disk. We'll have something that we're going to call a washer. And so if we think about our integration element here, our vertical rectangle right there at a random x, when that rotates around, it creates this washer. So there's our three-dimensional solid with, you can see the representative washer in each of these cases. And so the important thing in finding the area of a washer is that it's going to look a lot like the area of a disk, because it is. It's the area of a big disk minus the area of a small disk. Right? That little gap right there is going to be, this is going to be the radius for that small gap. So it's going to be pi r squared for the big outside disk, and then pi r squared for the little disk, and we just subtract the two. So F is representing the further distance to the axis of rotation, and G is representing the closer distance to the axis of rotation. Everybody tracking on that? So it's a disk minus a disk. And if this G was 0, then we're back to where we were on Thursday. We have a pi r squared where the function is representing the radius, and we have just one disk. All right. So let's see. We can do an example. Did we finish the last example we were doing on Thursday? Or now I'm all of a sudden.
I feel like not.
I feel like maybe we had one more thing on the last example. So before we do our washer example, let's just double check that. Did we have? Oh no, I think we finished it. Yeah, we finished. This was the last example. So we did finish it. We did finish it. Okay, good. All of a sudden was worried. All right, so here we've got our region in the xy plane. This is bounded by two curves, y equals x and the fourth root of x. The shape is going to, it's going to rotate around the x-axis and create this shape that's sort of kind of like a sideways bowl kind of thing. And that red segment right there, that representative rectangle, when it rotates around, it's going to create this washer. And we're going to think of the thickness of that washer as dx. So dx will be its thickness. So let's go ahead and set up our integral. One thing we haven't calculated yet is the limits of integration. We'll look at those in a moment. Let's just get the integral set up first. So the area is going to be the area of a washer, which is going to be pi multiplied by, and you can do you can sort of identify the radii in different ways. I like to just say r outer squared minus r inner squared. So for this first formula, whether it's a disk or a washer or a cross-sectional square or triangle, I'll just write down the generic formula for that object with r's, not x's or y's. So that's the area of a washer. Pi r outer squared minus pi r inner squared, and then we factor out the pi. Big disk area minus small disk area. And then we're going to convert over to x's and y's. So for us, when we look here, the outer radius is going to be dictated by the function that's further away. So this is going to be the outer radius, that distance right there. That is our outer. And that is given by this function up here, the top function. And so that vertical distance, that y distance, is going to be x to the 1/4. So that is going to go in here, x to the 1/4, and then we will square that quantity. And then the inner radius is going to be given by that distance right there. That distance, that y distance right there, is going to be given by x. So this will be minus x squared. And then we have our area function at x. If we check our extremities, that should give us areas of what? If we check our two extremities here. We check at 0 and we figure out what that intersection point is. We'll figure that out in a moment. What should the area be at those two extremities? What will be the area of the washer at those 2 points? Is there a washer at those 2 points?
No.
No, because the curves are pinching down to a single point, so when that rotates around, it's not creating a washer. So we should have an area of 0 at those two locations, that are two extremities. To figure out that point of intersection, maybe it's not too hard in this case, but let's just go through the math. If we want our intersection point, we set the curves equal to each other. So we're going to set the two y values equal to each other. The y value of the top curve is x to the 1/4. The y value of the lower curve is x. We can raise both sides to the 4th power here. This is a nonlinear equation, so our standard technique for a nonlinear equation is to bring everything to one side and factor. This tells us that we get x equals 0 or 1. Now, as soon as we raise an equation both sides to an even power, there should be a little bell going off in your head, a little warning that says you might introduce extraneous roots. Now, like if you have a very simple equation like x equals 1, how many solutions does that equation have? 1. But if we square both sides, we now have 2 solutions, so we've introduced an extraneous solution. Doesn't always happen, but it happens at times. So it's something we have to be aware of. We get 2 solutions here. We look, we see there's 2 intersection points, so all is fine. Those intersection points are going to be 0 and 1. And of course, we can check. Plug 1 into each, and yeah, we get 1. Plug 0 into each, and yeah, we get 0. So it matches. So that allows us to build our volume formula. We will integrate the area function from 0 to 1. And this 0 to 1 is on the x-axis. This is our domain down here. The domain is always perpendicular to your representative rectangle. The thickness of this representative rectangle is dx, which tells us we have to integrate with respect to x. So we will integrate pi multiplied by x to the 1/2, subtract off x squared dx. So we can factor the pi out and do our power rule for integration. We will end up with x to the, we add 1, so we add 2 halves. We get 3 halves. Divide by 3 halves gives 2/3. X cubed over 3, 0 to 1. Zero is not contributing any volume, so we don't really have to worry about that. We'll get pi, we get 2/3 minus 1/3. Oh. That's a great first problem. Shouldn't make a mistake with that arithmetic. So we end up with pi divided by 3 as our volume. Any questions? So the only difference here is that we have a slightly different cross-sectional area, finding the area of a washer instead of the area of a disk. Let's take a look at another one. So find the volume of the solid generated by rotating this region around. So we've got this parallelogram. We've got 4 different boundary curves to build this parallelogram. We're going to rotate it around the x-axis. We're going to get that shape. Our red segment right there, which is the random rectangle at x, is going to create that red washer. Once again, we are going to have to find the area of that cross-sectional shape. So we are finding the area of a washer. So the generic formula for the area of a washer, pi multiplied by r outer squared minus r inner squared. The outer function is the one that's furthest from the axis of rotation. It's that. That vertical distance, that y distance, is given by x plus 2. So that is what will be put in here. The inner distance is, it doesn't matter where we draw it really. How about right there? That's fine. It's going to be the distance, the closer distance to the axis of rotation. That y value is given by x. So we will have that. And if we simplify this, we will end up with the function pi multiplied by, actually I'll factor out a 4 just to simplify it a little bit. So 4 pi times x plus 1. That will be the area of the washer at x. If we check our left extremity, so when x is 0 right here, this distance between my fingers is 2. We plug in x equals 0 right there. Up here, this is the value of 2. So that would actually create a disk right there, right? Because it's touching the x-axis. And the area of that disk, pi r squared, so pi times 2 squared, so 4 pi. If we come over here and check, if we plug in 0 there, we get 4 pi. So our area predictor formula is giving us the right value there. Over here, it's a little more complicated. We'd have to do big disk minus little disk to find the area, and we could. What we see is that if we plug in a 4 there, should be 20 pi if you did it manually. But we'll assume our formula is right. And then to find the volume of this conical-ish looking thing, the volume will be the integral of the area formula. We can factor the 4 pi to the front. And then we have our integral symbol, which again is a big S because we're summing up small volumes to get the big volume. So in here you should be thinking about this as a volume. That is an area, and then this is a thickness or a width. So this is giving us a small volume in here. That's a W. So area times width is going to give us volume. And we do our integration here. We will have 4 pi multiplied by x squared divided by 2 plus x, going from 0 to 4. 0 is not going to contribute in this particular case. So we will have 4 pi multiplied by 4 squared is 16, divided by 2 is 8. 8 plus 4 is 12. So that'll be our volume. Doesn't seem too bad. Any piece of that you want to ask about? Seem okay? All right. So, more intuitive to rotate about the x-axis. We're used to integrating with respect to x. A little less intuitive when we turn things 90 degrees sideways here. So what we're going to think about is rotating around the y-axis now. We've got our generic formula, still looks the same. This is the area of a washer. It's just that we're going to use the p function to be the further function from the axis of rotation. The q function will be the closer function. But the same principle applies. Pi times p squared is the outer disk area. Pi times q squared is the inner disk area. We subtract the two and we'll get the area of a washer. And if the inner function is 0, so in other words, if the region is touching the y-axis, it will default to just a disk. So p of y squared. All right, so here's picture. This region we would call horizontally simple and not vertically simple. It's horizontally simple because no matter where we draw a representative rectangle, we have the same left curve and the same right curve all the way through. It is not vertically simple because you could draw 2 different vertical elements and have different bounding curves. Here, the top curve and the bottom curve are actually the same curve, which would have to somehow be split, which would be a pain in the neck. Here, we have the top curve would be just this little line segment, horizontal line. Bottom curve is this. So clearly not vertically simple. So we definitely have a horizontally simple region. So that's good if we're rotating around the y-axis. And this region, when it rotates around the y-axis, is going to create this cylindrical looking thing. And you can see our representative washer right there in the middle. So let's try one. So the first one we're going to do will default to disks. This region, this 2-dimensional region, when it rotates around the y-axis, it actually touches the y-axis, so the inner curve will be 0. So this representative rectangle, when it rotates around, is creating a disk and not a washer. So that q function is 0. Okay, so let's write down the generic formula first. We want the area of a washer. Area of a washer is pi times outer radius squared minus inner radius squared. Generic washer formula. When we look at our image here, the outer radius is that one right there, which again, the inner radius is going to be 0, so we can think of this as the outer radius or just the radius. If we instantly see that it's a disk, you could immediately just write this as pi multiplied by the outer radius squared. Let me just write this generically for a second because there's one thing we do have to do. So this function right here is 0 because we're touching the y-axis. So that inner radius is 0. Okay. Now, when we have a one-to-one function, so y equals natural log of x is 1 to 1. It's a function because it passes the vertical line test. And it's a one-to-one function because it also passes the horizontal line test. So a function that passes both the vertical and the horizontal line test. So horizontal line test means there's no horizontal line that meets this curve in more than one place, so it passes that test. It passes the vertical line test because no vertical line meets it in more than one place. So that means it's a function that is one-to-one. And a function that's one-to-one, you can solve for either x or y. You can present it as measuring y values, heights, or you could rearrange it, solve for x, and you'd be measuring distances that are horizontal. So when we write y equals x squared, we're thinking in our mind that it's presented as a y value. It's measuring y distances. But if we isolate x, then we're thinking of it as presenting as measuring something horizontal. This radius is horizontal. So we need to take the function that's measuring this horizontal distance and present it as an x value. So we look at this function right here. We want to isolate x. So x will be equal to e to the y. And we exponentiate. We put an e down here. So on the left we have an e to the y, and I just switched it because we usually put our independent variable on the right and our dependent variable on the left. So now the graph is the same curve. E to the y, x equals e to the y. That curve is the same curve as y equals natural log of x. It's just that here we're thinking of it as measuring vertical distances. You throw in an x and it measures the vertical distance. Here, you throw in the y and it measures a horizontal distance. So we've now taken this curve and created a formula that measures horizontally. That function is the radius. So that x distance is e to the y. So this is going to be pi times e to the y squared. So we get pi e to the 2y. So that is the area of our washer or disk in this case, because the inner radius is in fact 0. So the volume will be the integral of that function with respect to y. So that horizontal rectangle has a thickness of dy, which is a clue that we should have a dy and that we're integrating with respect to y, which means everything inside this integral, there can't be any x's in here. We cannot commingle x's and y's, not until Calc 3. We cannot commingle x's and y's inside of this integral. Now, limits of integration. They come from the y-axis. In this case, they're given to us. We see that this is y equals 2. We know the x-axis is y equals 0. So we're going from y equals 0 up to y equals 2. Those are the limits of integration. And that's our setup. So any question on any part of that setup? Now we have to integrate this function, this exponential function. And back in Calc 1, you would use your integration by substitution. But in this class, what we have seen is that there's a special case of integration by substitution that we call reverse chain rule. If you were doing regular old substitution, you would say, hey, let's let u equal the exponent. When you're doing substitution, you're generally letting u be the exponent, the angle in a trig function, stuff inside of a square root. If this is linear, that tells us that we can use RCR, reverse chain rule, if that's linear. We don't have to go through the 6 steps of substitution. We can cut to the chase. So the integral or the derivative of an exponential is itself. So that's the first thing we write down, itself. Integral or derivative of an exponential, is itself. And then we have to modify it. We have to tweak it by looking at the derivative of the substitution, in this case, the derivative of the exponent with respect to y. And the derivative of that exponent is 2. If we were differentiating, we would multiply by the 2. That's called the chain rule. But we are integrating, so we divide by the 2, and that's what we call reverse chain rule. So we divide by 2. And then we have our limits of integration. So we will have pi halves. In this case, the 0 does contribute some volume, or it takes away some volume. We don't get to ignore the 0 here because e to the 0 is not 0. E to the 0 is 1. So we have to be a little more careful here. So I've factored out this stuff. And now the 0 and the 2 get plugged into the remaining function, upper limit minus lower limit. So let's plug it in. We will get e to the 4 as the value for the upper limit, minus e to the 0, and e to the 0 is 1. So here is our volume right there. So that is our exact volume. And if the book said approximate to the nearest tenth or the nearest hundredth or whatever, we would plug it into our calculator to get an approximation. So that is exact. When you plug it into your calculator, you're getting an approximation. You're getting an estimate. Typically in here, we want exact values, so we leave it like that. We leave the e, we leave the pi, we don't approximate. But every once in a while in an application, they may say round to the nearest tenth or hundredth, then you plug it into your calculator. All right. Yeah?
So you were talking about functions. In this case, it passes the vertical line test, horizontal line test.
Yeah, so it's a one-to-one function.
If we're dealing with functions that fail those tests, do we just work around it by restricting the domain or
Yes.
piecewise functions?
So if we have something like a circle, right, a circle is neither one-to-one, it's not a function and it's not one-to-one. So we would have to restrict ourselves. And we'll see a few examples of that in a little bit where we have to somehow restrict the domain. So if we have a circle and we're rotating around the y-axis, we're going to look at the left and right sides, the left and right semicircles. If we're rotating around the x-axis, we would have to look at the upper semicircle and the lower semicircle. So yeah, it's exactly what we'll do. If it's not one-to-one inherently like this, then we have to somehow look at a piece of it that is one-to-one. All right, so let me just remind myself of one thing here. Yeah, okay. So I'll do this one, and then you guys can try the next one. So we'll do a bona fide washer one now. When we look at our region, this region is bordered by 3 curves to build that triangular region. It's going to rotate around the y-axis, and we're going to use a washer. The outer radius is that one. So it goes to the function that's furthest from the axis of rotation. The inner radius goes to the function that's closest to the axis of rotation. So here we are going to get a bona fide washer. So the area of this washer, we will have our generic formula first, just to sort of think about the geometry. And then we have to figure out how to present these functions. Both these curves are one-to-one. They both pass the vertical and horizontal line test. The way these curves are described here, they're described as measuring, those functions are measuring vertical distance. Well, clearly this red representative rectangle is sideways, it's horizontal, so we need to change the way those functions are presented. Instead of presenting them as measuring height, we want to present them as measuring distance sideways, lateral distance. So this one is pretty easy. We just do that. Now we've presented it. So up here in this original presentation, x is on the right, which means it's the independent variable. Y is on the left, which means it's the dependent variable. Similarly, up here, x is on the right, so it's independent. Y is on the left, so it's dependent. When we switch this perspective to measuring horizontal instead of vertical, we're changing the independent variable. So up here, when we isolate x, we get y divided by 2. So now y is the independent variable. X depends on y, so we call it the dependent variable. Now we're measuring horizontal distance for both those functions. So the outer function, right there, this horizontal distance, this x distance, is given by y. So we get y squared. The green distance here, the inner radius, is given by y over 2. So this will be y over 2, quantity squared. And again, in your mind, as soon as you see that horizontal rectangle, you should be thinking the thickness is dy. So that tells you you're integrating with respect to y. That tells you everything that you plug into your generic formula should be y. You should be plugging in y expressions. And then we hop down to our volume. We will have y squared minus y squared over 4 dy. And then our limits of integration are coming from the y-axis. And they tell us that our upper curve is y equals 6. And these two diagonal curves both go through the origin. These diagonal lines. A line is a curve, these curves, these lines, whatever. So our limits of integration are going from 0 to 6 on the y-axis. So that is our interval right there that we're integrating over. So 0 to 6 on the y-axis. Then we can do some simplification here. Let's factor out the 4. So I'm going to multiply this one by 4 over 4. Factor out that 4 in the denominator. We'll give pi fourths out in front. And then we have our integral symbol. And so that 1/4 is coming out. What's left is 4y squared minus 1y squared, which is 3y squared. Get that. We'll factor out the 3, giving 3 pi divided by 4. And then we'll integrate the y squared, getting y cubed divided by 3, 0 to 6. Threes will cancel here. And we will be left with pi over 4. And here the 0 is not going to contribute anything. Plugging in 0 gives 0. So we only have to worry about that 6. We're going to get 6 cubed up here. 6 cubed is 216. Maybe it's easier to just write it as 6 times 6 times 6 for a moment, because we're going to have some cancellation here. 2 makes that a 3. That 2 becomes a 1, and that becomes a 3. Whatever works easiest for you. So then we have 9 times 6. That'll be the volume. Good? Great. We'll see. It's your turn. You get to try now. Unless someone has a question on any of the ideas here. All right. So let's go to the next slide. So you all try this one. Similar idea. We've got our region in the XY plane. We're going to rotate it around the Y-axis. I sort of indicated our inner and our outer for you. So go for it. Find the volume of that solid of revolution using washers. Nice color. Did you print them out here or did you?
No, I printed them at home.
Oh, at home, okay.
Yeah.
So you can also go to Kinko's and take all those files to Kinko's and they'll print it all out and find it for you.
Really?
Yeah.
Maybe I'll try that.
Yeah. Kinko's or the other one. What's the other one these days? Is it? Not. Yeah, there's some other one, some other place that prints out shop. I can't remember if Kinko's is closest to us. Or, yeah, if you take all the notes on a flash drive, they can print out the whole packet, the whole pile of pages, and put them in the binder for you. Let me know if you have a question. Let me know if you're stuck. Remember that you have to change your functions to be presenting as horizontal rulers. Actually, maybe I'll do roll now.
I do have a question.
Yeah, sure.
So, which part?
Oh, I see a typo. Thank you. Thank you. There is a typo. Oh, that's in your notes. That's not up here. I fixed it. That should be y equals natural. That should be y equals square root of x.
Okay.
Yeah. So there's I've got to go update that PDF file then. Yeah, that should be y equals square root x, not natural log of x. Nice catch. Would natural log of x, out of curiosity, would it go through the origin? Y equals natural log of x? Is the origin a solution to y equals natural log of x? No. If we were dealing with y equals natural log of x, remember that would be over, there'd be an asymptote here, and it would pass through right at 1 if it was a natural log function. Natural log of 0 is undefined. All right, let me do roll. Samuel? I've not heard from him. Maybe he's not going to be in this class. Corey? Marley? Benjamin? Tegan? Anthony's in Florida. Noah. Zachary. Connor.
Here.
Bradford.
Here.
Macy. Mia.
Here.
Violet. And Eva. Jesse is sick. Marissa. Shelby. Christian. Also another no-show. Enzo. Enzo? Enzo? Okay, Victor is here. And Cullen, not here either. Justin. Lance. Colin is here. Elena. And Lynn. All right. Looks like we might have 4 no-shows. Wow. I haven't heard anything from those folks, I don't think. Small class. No complaints. Anyone stuck or need a nudge? Yes. Let's see, so when we rewrite that, we're gonna, when we saw, so first off, yes,
Okay.
yes. Because when we look at that rectangle, it's sideways, so it's going to be a dy, not a dx. And if we know we're going to have a dy, that's a clue that everything in here has to be a y, because we can't put a dy with a bunch of x's. So we want to isolate x in that square root function, solve for x. Mhm. Yeah. Yeah, sure. So the outer radius, I'll write that for a second, is the function that's furthest. We're rotating around this axis. So the outer radius is the function that's furthest away from there. So that distance right there. And what is that distance? Let me ask you that. Let me ask you this. If I wrote, so we can, these are just representative distances. So we could draw it there, we could draw it there, we could draw it here. Do those distances change? Yeah. Right, that distance is going to be 4 no matter where you do your representative outer radius. So that distance is always 4. And then the inner radius, that's going to go from here to here. That function was y squared, and the only thing you have to make sure you do is square that. Because our outer is this, and our inner is that. Make sense? Good? Is that the right answer? That's the right answer. We'll find out, right? We'll find out real soon. Let's do it. Let's find out if it's the right answer. Okay, so a couple of things initially. The distance is horizontal, so we have to have a dy, which means we have to isolate x for those functions. Okay, so the function on the right, it's already isolated. Right? We've already got it written as an x equals thing. Right here, this is going to be rewritten as x equals y squared. So now it's measuring horizontal. We are getting a washer. So the area of our washer, our generic formula, pi times r outer squared minus r inner squared. Let's put that there and that there. So there's our generic formula. We look to our outer radius. That distance is 4. Right? That's the x value there. This x distance is 4. And it doesn't matter where you draw this representative radius, you have a constant of 4. So that is what's going to drop in here for the outer radius. And then for the inner radius, we want this x distance. So here's the thing that's giving us x distance, and that's the value of the x distance right there is y squared. So this will be y squared, but then that is squared from our formula above. So the inner radius is this distance here to the square root function. To measure horizontal, we isolate x. So this x distance is given by this value. That's the value of x here. This is the value of x on the right. And that will give us a formula for the area. This will tell us the area of the washer at y. So if we know what this point is up here, what is that point? 4 comma what? 2, because that's a square root function. So if we put in a y value of 2, should there be any area? No, because there's not a red segment right there. That red segment becomes 0. So we should get 0 in this formula over here if we plug in y equals 2. If we plug in y equals 2, we in fact do get 0. So most likely we have the right area formula. If we want to check the lower extremity, this distance right here from all the way across is 4. So that is no longer a washer. It's going to be a disk of radius 4. Pi radius squared is 16 pi. When we plug in a y equals 0 here, do we get 16 pi? Sure enough, we do. So for that formula to give the correct values at the endpoints and not be the right formula is very unlikely. So we're on the right track. Volume is the integral of area. So we will integrate our area function. Our domain is coming from the y-axis. So we're looking over here. So all these y values are in the domain. All these y values are creating washers, except for the upper one and except for the lower one. Get a disk and a nothing. So 0 to what? 0 to 2. So the y values, right? We're coming from the y-axis. The y-axis, the y value down here is y equals 0, all the way up to y equals 2. So 0 to 2. We can now integrate. This will give us 16 multiplied by y minus y to the 5th over 5, 0 to 2. And when we look at that, we see 0 is not going to contribute anything. Plug it in 0, get 0. So that allows us to focus on just the upper limit of integration. Plugging in the 2 is going to give us 32 minus 32 fifths. Arithmetic. Eek. My strategy, factor out the 32 and give us something, give us some fractions that we can do in our head. We know that 1 minus a fifth is 4 fifths. 5 fifths minus 1 fifth is 4 fifths. So this will be 32 multiplied by pi multiplied by 4 fifths. 5 does not go into 32, so this is going to be 128 times pi divided by 5. Look familiar? Hopefully it looks familiar. Hopefully. So if you didn't get that right, do you see what you did wrong? And will you never do it again? Or at least not until Calc 3?
Wait, why is that supposed to look familiar? 128.
I'm hoping that that's the answer you got when you were doing it on your own.
That's what you're saying. Familiar.
And that you didn't come up with like 605 divided by 17 square root of 2 or something. But if you didn't get that answer right off the bat, do you see what you did where you went awry? So there's quite a few geometric principles going on here, and it can be very dyslexia invoking, this whole, do I solve for x or do I solve for y? Which comes, how do you, somehow in your brain you've got to orient and think about the way functions are presented and recall back in the day when you were told which letter was the independent variable and which letter was the dependent variable, it didn't really matter. Right? It was just a piece of terminology that you never really used the fact that x was independent and y was dependent. You just knew you could plug in x's and get y's. And if you had to plug in y's, you could solve and get x's. Here it becomes a little more important to sort of understand the mechanics here. When we write it like this way, in this form, x is dependent on y. So this function is a function of y, not a function of x. This is a function that's measuring horizontal distance, and this is the value. Right, so the right-hand side we think of as the value of the function. This is going to be the value of the x distance, whereas that's going to be the value of the x distance, whereas this is the value of the y distance. Okay. All right. Now that you've got that mastered, let's mix it up. Let's throw in a little curveball, or a knuckleball even. Instead of rotating around the x-axis or the y-axis, let's rotate around a random axis. Not so random that it's diagonal. That you could do when you get to Calc 3. You could rotate a region around a diagonal axis using vectors, which is quite the entertainment. Here we'll at least keep it parallel to one of the coordinate axes. All right. So we're going to take this shape that's bounded by these three curves. So these three curves create one and only one region. And we're going to rotate not around a coordinate axis, but around the line y equals 1. So all of our geometric principles still hold. One important thing to remember is that when you find a vertical distance, it's upper y value minus lower y value. That's how we find a vertical distance. And a horizontal distance is the right x value minus the left x value. So we have to keep these basic geometric principles in order. So first off, when it rotates around the line y equals 1, our region is touching that axis of rotation. So we will get a disk and not a washer, because it's touching the axis that it's rotating around. So as it's rotating around there, it's going to create a disk. I've drawn a representative vertical rectangle here. So when that vertical rectangle rotates around, it's going to create that disk. The thickness of the disk. Is the thickness of the disk dx or dy? Dx. Vertical element, vertical rectangle, thickness is always dx. Horizontal, thickness is always dy. All right. So there is the radius of our disk. Generic formula for area of a disk, pi r squared. That's our generic formula. Now, we already have in our head that we have a dx, so we know that we need to replace that r with x's. So let's take a look at our picture here. So this upper curve right there, that's y equals 1. This lower curve right there is y equals 1 minus square root of x. This red rectangle, red integration element, whatever you want to think of it as, it's vertical. So we need to figure out, so that means the functions that are bounding it need to be written as functions that are measuring vertical distance. And they are, right? These are both solved for y, so these are measuring vertical distances. So that red segment, its length is the upper y value, 1, minus the lower y value, 1 minus root x. That is r. So r is the upper y value, 1, minus the lower y value, 1 minus root x. And then we square the radius. So that distance right there, this is r, right there. Upper minus lower. We're up here at 5 and down here at 1. 5 minus 1 is 4. Now we've just generalized that. This upper y value is a number. This lower y value is a function. So we just do the subtraction. We've generalized distance. So we're going to simplify this. So a pi multiplied by. When we distribute the minus sign here, we'll get a 1 minus 1. The 1's will cancel. We'll get a positive square root of x. And then we square that positive square root of x, and we get just x. So So this is our area function. So that's measuring the area of the disk at x. Let's check our two extremities. When x is 0, how big is that disk? 0, right? It's just a point there. So this representative rectangle, as we get closer and closer here, right? It's getting shorter and shorter and shorter until we're right there and it's just a point. So we get a disk of no area. It's not really a disk, it's just a point. Okay? Let's check the other extremity. The other extremity, x is 1 over here. What should the area of the disk be when x is 1? Pi 1 squared is pi. If we plug in 1 here, yeah, we get pi. So it's checking at the two extremities. So we're on track. The volume is the integral of the area function, dx. The limits of integration we can see from our graph here, 0 x value here, and we are integrating this way on x, so 0 to 1 from the x-axis, not the y-axis. So we will get pi and then x squared over 2 from 0 to 1. 0 does not contribute, plug in a 1, and we get pi divided by 2. That will be our volume. So when we rotate around a random axis, we still are thinking with basic principles. Horizontal distance, right minus left. Vertical distance, upper minus lower. Question?
No.
Anyone? Question? All right. So our next one will be this one. Let's go ahead and we'll take our break now, and maybe you can think about this during the break, and we'll attack it in 10 minutes. So we're at 2 minutes before the half, so 10 more minutes, and then we'll attack this one. Pause the recording. But you will work. So this is going to be our region in the xy plane. It's bounded by 3 curves. And we're going to rotate around x equals 4. So axis of rotation is there. We are using washers. If we think about our horizontal rectangle right there, when it rotates around that axis, there's a gap right there, so it's going to create a washer. So let's write down our generic washer formula. Area of a washer, pi multiplied by outer radius squared minus inner radius squared. So when we see that horizontal rectangle, one of the first things that should come to mind is that we are using d what? dy. So we think of that dy as measuring the thickness of that red rectangle. So that's the thickness of it. So that's an important clue. We also see that it's horizontal, so that means that our functions that are the boundaries of that rectangle need to be measuring horizontal distances. That means that they have to be in a form where x is isolated to the left. All right. When we look at this outer curve here, so I'm going to look at our axis of rotation. The outer curve is here. What is the equation of this boundary curve?
0.
X equals 0. It's a function. So x equals 0 is that outer, let me not write it there. Let's write it over here. So this curve, this line, has an equation, x equals 0. X is isolated already, so that's good. Now when we look at the right-hand curve, which will be dictating the inner radius, so this curve right here, that curve is y equals square root of x, but we need to write it as x equals y squared. We need to isolate x because we're measuring horizontal. So we need to write that function with an x isolated. So now we're good to go. We look here, our outer radius, so that's the blue. What is that? Distance. 4 minus 0. Right? So that blue line I have there is horizontal. The length of it is the right minus the left. The right x minus the left x. The right x is 4. The left x is 0. So this distance is always 4. And no matter where you draw across, that distance is always going to be 4. This is the left curve, the left boundary, and its distance to the axis of rotation is always 4. So that will be 4 squared. The inner radius is the purple line here. It's also horizontal, so we have to do right minus left. Right minus left. The right x value is 4. The left x value is y squared. So 4 minus y squared squared. So the outer radius is the blue line. The blue line is horizontal. Anytime we have a horizontal line, we do the right x minus the left x. So if I ask you how long is that blue line, you say, well, the right x is 4. The left x is 0. So it's 4 minus 0, which is 4. There's no variable there, right? These two lines are parallel, so they're always 4 apart. When we go to find the length of the purple line, it's a horizontal distance, so it's the right x minus the left x. The right x is 4. But the left x is variable. It changes depending on how high you are here. It depends on the y coordinate, the y value. So 4 minus the x value is y squared. So that is our washer area. If we simplify this, we will get some 16s that cancel. So our simplified formula for the area of this washer, those 16s cancel, this minus distributes. I'll write it in descending order because it's kind of what we like to do when possible. Until we get to infinite series, then we'll write it in increasing order. Any questions up to that point? So let's think about our two extreme cases for a moment. When we think about our horizontal rectangle here, and we slide it all the way down to here to 0, what should be the area of the washer? 0. So if we plug in 0, we should get 0, and we do. If we look at the other extremity up here, when our red rectangle slides all the way to the top, the length of that red rectangle is 4. It's now a disk instead of a washer, so the area should be pi 4 squared, so that's 16 pi. When we plug in 2, do we get 16 pi? Well, we plug in a 2 here, we're going to get 32 minus 16, so yeah, we will get 16 pi. So it's correctly finding the area of the washers at the two extremities. So we are good to go for volume. Volume will be the integral of the area function. So we get pi integral and when we look at our limits of integration, they're implied. We're told that we're going up to 2. So we are integrating with respect to y. So we have washers for all these y values from 0 up to 2. Perform our integration using the power rule. So we will get minus y to the 5 over 5 plus 8y cubed over 3 from 0 to 2. 0 is not going to contribute in this case. No volume coming from the 0. Plugging in the 2, we get minus 32 fifths plus 2 cubed is 8, so we're going to get 64 thirds. So we definitely are going to have to get a common denominator. Let's factor out a 32 though. So let's do a 32 pi. And then the common denominator is 15, so we're going to multiply this one by 3, but we pulled out the 32, so it's going to be minus 3/15. Minus 3/15. And then this one we pulled out a 32, so there's a 2 left there. We have to multiply it by 5, so plus 10. So that will be 32 multiplied by pi, multiplied by 7/15. 32 and 15 have nothing in common, so we just have to multiply this all out. So we get 15 there, we get pi there, that's 14, carry the 1, 22. Any questions? That is a funny looking 3. All good? Let's take a look at a torus or a donut. If you like voodoo donuts, you can find the volume of your voodoo donut using this technique. So a torus is generated by taking a disk and rotating it around an axis. And the question is, well, what's the volume of that three-dimensional object, that torus? Well, the example we're going to look at, we've got this generating disk of radius 2. And the center of this disk of radius 2 is right here on the x-axis at 3, 0. Okay, so now this gets the question that Lance brought up. This disk is not a function. So we are going to have to break this disk apart. We are rotating around the y-axis, so we need to be measuring horizontally. And so what we need to do is bust it apart so that we have the right half of the circle, the left half of the circle. The equation of the circle in general, circle of radius 2 centered at 3, 0 is right there. From algebra, your equation of a circle centered at a particular point. Well, if we want to isolate x in this equation, we subtract off the y squared, we take the square root, and we get a plus or a minus, and then we add 3. So that's going to be the right half of the circle, that's going to be the left half of the circle. So we have those two semicircles. When we rotate our sleeping rectangle, our horizontal rectangle, when we rotate that around the y-axis, we get a washer. We definitely get a washer, right? There's a gap. Right there's the gap. So when it rotates horizontally around that axis, we are going to get a washer that's flat. So we know that the area of a washer, we've got our generic formula down pat by now. Pi multiplied by r outer squared minus r inner squared. It's going to be a dy because it's horizontal. Thickness of a horizontal rectangle is dy. So we look here. Let's go with the outer one. The outer one is a horizontal distance. Horizontal distance, right x value minus left x value. This is the x value right here for the right-hand curve. This is the x value for the left-hand curve. So for the black distance right there, that distance is the right x minus the left x. The left x is 0. Right, x equals 0 is this axis of rotation. So our outer radius squared is going to be this mess squared. There's our outer radius squared. The inner radius squared is this orange distance. Again, it's horizontal. So it's right x minus left x. The right x for this horizontal is that. The left x value for that horizontal is once again 0. Okay, this is x equals 0. So now we're going to have minus the inner radius, which is this minus 0, so just this, and we square it. We have that. Now we get to do some fun foiling. Okay, so FOIL, we're going to get 3 squared. That's first squared, which will be 9. We can do 3 squared in our head. 9. Plus, because this is a plus, a times b. Remember that your general foiling formula, always important to have this down. That is a squared plus 2ab plus b squared. And if we FOIL a minus b, we will get a squared minus 2ab plus b squared. So in our situation here, there's a, there's b. So a plus b, quantity squared. So the middle term is going to be a times b doubled. So a times b is just these two multiplied together, and then you double it. So we get 6 square root of 4 minus y squared. And then b squared, we square the square root, and it goes away. So there is a plus b squared. And then minus that. Let's keep that in parentheses and not try to distribute the negative 1 and FOIL it at the same time. Hopefully you can do that, but we will make less mistakes if we don't try to do that. So here we have a and then minus 2ab. And then once again, we're going to multiply by plus b squared. So plus this thing squared is going to be 4 minus y squared. We have all that. And then there's a bunch of cancellation. So we will have pi multiplied by, let's see what cancels. So this is going to be a negative 9, so that guy's going to go away there. That minus sign distributes to that 9, so that one's going to be a negative. It's going to distribute to this 4, making this a negative 4. So that and that are going to go away. And then this negative y squared, this minus distributes, giving a positive y squared. So that is going to go away also. That and that will go away. So we don't have a lot left. We have 6 times the square root. Minus a minus is plus 6 times the square root. So we have 6 times the square root plus 6 times the square root, which is 12 times the square root. So we'll have 12 root 4 minus y squared. And that will be our area. And let's see, what did I say up here? I want to just point this out. Use geometry to evaluate the integral. Any questions on getting that area function that we will then have to integrate to get to the volume? So that's our area function. And if we check our two extremities, when y is up here at 2, or when y is down here at -2, we will get 0. Because the horizontal rectangle is shrinking to 0 there, and it's shrinking to 0 down here. So at -2 for y or +2 for y, we should get 0 for the corresponding washer, which is not really a washer because that inner thing shrunk to 0. Okay. Now here is the issue. You can write this down very easily. You can say, oh, okay, we just integrate the area. Now, we could go from -2 to 2. What else could we do? We could use symmetry and go 0 to 2 and double it. So whenever we can in calculus, we love using symmetry. So let me do this. Put a 2 right here in front. So this is by symmetry. So that's our sim2. So that's by symmetry. And we will go 0 to 2 instead of -2 to 2. The hardest part about calculus 2 and 3 is recognizing when you can and when you can't integrate a function, a given function. You cannot integrate that function. The only technique you have at your disposal right now is integration by substitution. If you were to let u be what's inside the square root, which would be the natural thing and the only thing that might work if substitution was going to work, if you were to let u equal that, its derivative is -2y. And there's no y on the outside to swallow up the y that you get from that derivative of your u. So if we change that integral just a skosh, if we made that the integral, if we made it this, if we had a y out there, no problem. You can do it. You can just change this. The hardest thing is that in Calc 1 with derivatives, I can make the nastiest looking function you can imagine. Multiplication, exponents, fractions, composition, does not matter. You all have the skills to integrate, to differentiate any function I could possibly create. As long as you know the individual derivatives, you can differentiate anything. Integration, not the same. With integration, you've got to go through your toolkit of integration techniques, and then sometimes none of them will work, and you have a function that's not integrable. So that's what makes integration so much harder. It's kind of like when you were learning multiplication and division. Multiplication is no problem, right? You can always multiply, but dividing, sometimes there's no common factor, and you just have to leave it as a fraction. It's that kind of thing. Division was always way harder than multiplication. Integration, way harder than differentiation. That is not integrable. Like I can take a simple thing like e to the x. You know how to integrate that. I make one tweak, and I make this e to the x squared. This you can integrate, no problem. That you cannot integrate. Again, if there happened to be an x in front of it, like that, then you can integrate it because you could use substitution. You could let u equal x squared. The derivative of x squared is 2x. And if there was an x in front to suck up that x from the derivative, you can integrate it. So this is the thing going forward that you really have got to pay attention to. If something is integrable, why is it integrable? If it's not integrable, why is it not integrable? You've got to sort of start figuring out how to go through this process of triage in your mind. What are you going to do when you see an integral? Now, the next thing, it's kind of tricky, is that an integral represents a geometric idea. And I created a handout that I'm forgetting if I put it, I think I put it in this review here, right here. If I were you, I would go through this handout and make sure it all is crystal clear. This is a summary of stuff that you did in Calc 1 that should be crystal clear. If we want to find the area here, that's the formula. It's not integrable, but you know that this formula here is finding the area of that semicircle. This is the right side of a circle of radius 4 centered at the origin. And if you integrate the right side, you get the area between the curve and the y-axis. You get that area, which is going to be 8 pi. Circle of radius 4 would have the full area would be this times 2. The area of the semicircle will be 8 pi. So I would go through all of these. I've broken it apart so you have a right function, a left function, a top function, a bottom function, and created the corresponding integrals. And all these are finding areas of semicircles. So if you know what your integral is representing geometrically, sometimes the geometry is easier than the calculus. Other times, the calculus is easier than the geometry. So this is going to be an important idea. So let's go back to where we were and see if we can figure out the geometry of this integral. So let's take a look at just the integral. So what function are we integrating? We are integrating the function x equals the square root of 4 minus y squared. That is the function we are integrating. What is that? That's a semicircle. If it's not 100% clear to you that it's a semicircle, then do this. Square both sides, add the y's to the left, and you've got that after you square both sides. So you go to the picture. That's a circle centered at the origin of radius 2. All right, circle centered at the origin of radius 2. Looks roughly like that. Now we come back up here to the function. This function has x isolated. So is it the right half, the left half, the top half, or the bottom half? This is the right half because x is positive. So this is x equals positive 4 minus y squared. The left half would be x equals negative square root of 4 minus y squared. The top half would be y equals the positive square root of 4 minus x squared. The bottom half would be y equals negative square root of 4 minus x squared. So go to that handout and play with your semicircles and make sure you have your semicircles down. So now, this integral, there's 2 up there, there's 0 there, there's negative 2 there. This integral is only going from 0 to 2 with respect to y. So that integral is finding the area between that curve and the y-axis on the interval from 0 to 2. So this integral is representing a quarter disk. This is representing the area of a quarter disk. That's what that integral represents. It's finding the area right there. All right, so this whole thing becomes 24 pi area of a quarter disk of radius 2. Well, the area of a full disk of radius 2 is pi r squared, but we want a quarter disk, so we divide by 4. So when all is said and done, our volume becomes 24 pi squared, because those 4's cancel. This is a 4 in the numerator, and that cancels with that one. So there are times where we need to use our geometry to evaluate an integral, because the function in the integral is not integrable. Okay? So look at that worksheet, play around with those semicircles. A lot of it is just a little bit of practice to get familiar with semicircles and how you move the square root around. Any questions on any piece of this whole torus thing? So it's a good one to fiddle with. Understanding this problem means you are understanding a lot. This is sort of a very comprehensive problem, that if you can understand all the details of this, you're flying. Flying on math. Flying on math is so much better than flying on other things. All right. Let's go to our third and final geometric cross-section. Well, I guess we've had 4. We did the generic slicing, and then we did discs, then we did washers. Now we're going to do shells. So it's the third of our sort of named cross-sections. So cross-section in this context is in quotes, because normally a cross-section means you're slicing it with a plane. You're getting a 2-dimensional cross-section. Here, cross-section in quotes, let's think about the geometry. That region, 2-dimensional region, it's rotating around the y-axis. It's creating this bell with a hole in it. So instead of using, now you could use washers here. If you rotated this around the y-axis, you could use washers, but you would have to break it apart into 2 separate regions, because the right-hand curve here is a constant, x equals b, whereas the right-hand curve here is x equals some wiggly thing. So you could do it with washers, assuming you could isolate this function. You could isolate this function for x. But what we're going to do instead is think about using the apple coring idea. So the idea is that we are going to create cylinders that are all nested, and we're going to fill up the volume by stacking, by nesting these cylinders. So instead of stacking discs or washers, we're sort of doing this nesting idea. The area of a cylinder is the circumference of the base, 2 pi r, multiplied by the height. That's what this is representing. 2 pi r, so this x point right here is representing the radius of the cylinder at x sub k star. So that distance right there, that is the radius of the cylinder if you were to rotate that around. So 2 pi r, this is circumference right there. That is circumference. And then let me not get the f in there. So circumference is up to there. And then f of that value is the height of the cylinder. So this guy in here is height. And then that is thickness. So all that means this is the miniature volume. It's the volume of one of those cylindrical shells. So it's kind of like when we go from a cross-section to a slice when we add thickness. Same idea here. If you look at everything but the delta x, you've got the area of a cylinder, but then the dx or the delta x adds thickness to it, so it's kind of that conversion from a cross-section to a slice. We call these things cylindrical shells, so you can kind of think of the shell as having some thickness to it. And that's a Riemann sum. As n increases, as you get tighter and tighter and tighter cylinders, you get you fill out the whole entire volume exactly when you take the limit. So the limit of that Riemann sum, once again, is going to be an integral. So the limit of the Riemann sum will be the integral, and it's circumference times height times dx or dy. So that's what's happening. More and more cylinders. We take the limit of our Riemann sum, and we get a definite integral. Once again, in this definite integral, this part right here is circumference, this part is height, and that part is thickness. So and then the integral symbol's like an S for summing. So this gives us the volume of one shell. We add them all up, and we get the total volume. All right. So if we generalize the height piece, if the function is just going down to the x-axis like that, then the height of the cylinder is whatever the function is, f. But if the cylinder's up here and there's this gap between the bottom of the cylinder and the x-axis, then this height, vertical height, is f minus g. All right, so this is just measuring height right here. So f minus g, that's height. Height of the cylinder. All right, so when we think about our generic shape here, our generic shape is a cylinder, and the area of a generic cylinder, 2 pi r h. Bless you. 2 pi r circumference, h is the height, so 2 pi r h, area of the cylinder. All right, let's try it. Let's go to town. So we've got a region in the xy plane. We're going to rotate it around the y-axis. And here's where we notice our first major difference between disks, washers, and now shells. Notice that our rectangle is vertical. Our rectangle is parallel to the axis of rotation. It is not perpendicular. Disks, right? There's your rectangle here. There's your axis. That creates a disk. It's perpendicular to the axis of rotation. If there's a gap and it rotates, it's still perpendicular to the axis of rotation. But to create a cylinder, your rectangle and your axis have to be parallel to create a cylinder. So that's the major difference between disks, washers, and shells. Your element, your rectangle, it's got to be parallel to create the cylinder. So this way or this way. All right, so that's the first thing we notice, is that our axis of rotation and our rectangle are parallel. So we are going to use a cylinder. We have the area of a cylinder or a shell, whatever subscript you want to put. Area of a cylinder is 2 pi r h. 2 pi r, circumference, multiplied by the height. Gives you the area. Are we going to use dx or dy? Dx. Whenever, no exception. If you have a vertical rectangle, it's always dx. Horizontal rectangle, always dy. No exception there. All right. The one wrinkle, the one exception that we see is that our axis and our rectangle are parallel. This is the one thing that changes. But they have to be parallel. But regardless, once you draw your rectangle, if you draw it vertical, it's always dx. If you draw it horizontal, it's always dy. Okay. So when we look at our curve here, this curve, which is right there, that curve, y equals, let's write it as 1 over 1 plus x squared. So that curve is measuring height. The way it's presented, that function is measuring height. We've isolated y, so it's measuring height. That's good, because this is the height of our cylinder right here. That is measuring height. So we don't have to change anything. We don't have to solve for x. No funny business there. So we're going to have 2 pi. Now here's the trickiest piece of them all. R. So you're imagining this red rectangle rotating around, creating a cylinder of radius what? What is the radius of the cylinder created by that red segment? X. Right? Isn't that what this generic X means? That X right there, if I say this is the vertical rectangle at X, doesn't that tell me that we are X units from the y-axis? Right? That's what that X means. If I plop an X down right there, we are X units from the y-axis. If you plop a Y down right there, you are Y units from the x-axis. So we are X units from the y-axis in this case. So that distance right there is X. All right, and we want everything in here to be X's because we know we have a dx. So that tracks very nicely. So that is our radius. That's the radius of the cylinder at X. And the height is the function that we have right there. So now we have the area of the cylinder at X. If we plug in 0, we have no real cylinder, so we should get an area of 0. Right? If we draw that rectangle right here, it rotates and it's just spinning around. We should get 0, and sure enough, if we plug in 0, we get 1 here, 0 there, 0 times 1 is 0. Okay, so that works. And the cylinder that we get out here, the radius would be 2, so we would plug in a 2 there, and we would get 2 pi r times h. We'll get the right answer. So volume. Volume is the integral. And I am going to be creative here, and I'll explain why in 1 second. I am going to only factor out the pi. Up until this point, we've just sort of factored out the entire constant. But let's not do that in this case. I'll show you why in a moment. It won't really matter if you did factor out the 2, because you can always put it back in. How about limits of integration? What do you think? 0 for sure. Should we be looking at the x-axis or the y-axis?
X-axis.
So the element is vertical, and it's sliding through x's, right? We're drawing these vertical rectangles at particular x's. So we want to say to ourselves, well, where are all these rectangles living? They're living from x equals 0 to x equals 2. Very similar to disks and washers, right? Your domain is always perpendicular to that sliding rectangle. It's sliding from x equals 0 all the way through to x equals 2. So this should be 2. We're integrating with respect to x, so the domain should be coming from the x-axis. Now integrating this. You only have one technique of integration right now. You're going to have a ton after this class. But at this moment, the only technique you have, other than if you know the antiderivative, is substitution. So that is not the derivative of some function you happen to know. So we think, OK, substitution. When we use substitution, we are going to let u be what's in the angle position, what's inside the square root, what's in the exponent. And in the case of a fraction, often you're going to let u be what's in the denominator. When you look at that denominator and you think about its derivative, what is the derivative of that denominator?
Arctan.
The integral is arctan. Right? The integral of 1 over 1 plus x squared is arctan x. But what's just the derivative of just the denominator?
2x.
2x. Right? So the denominator's derivative is 2x, and that is present. That's when u substitution works. If you choose something for u, its derivative has to be somewhere in the integrand for it to work. So that's what we're going to do in this case. We're going to let u be 1 plus x squared. So du will end up being 2x dx. And that is what's in the numerator right there, 2x dx. When we do substitution, all the x's have to turn into u's. And so that derivative of our u has to be present, has to be in there somewhere. All right? So we plugged in u for the denominator, 1 plus x squared. And then that whole numerator, 2x dx, that's all going to be replaced with du. All right? Limits of integration. Limits of integration from your substitution step. That substitution tells you how to convert x's to u's or u's to x's. Right, that's what that formula up there is, right? It takes you back and forth. That's how you exchange x's and get u's. So you plug in an x and get a u. This x is 0, so what's the corresponding u? That x is 2, what's the corresponding u?
5.
Bingo. So that's our new integral. We've exchanged all our x's for u's. We've exchanged our x limits of integration for u limits of integration. Now we're good to go. That is a recognizable integral. You learned that in Calc 1. That is natural log of absolute value of x, in this case u, from 1 to 5. Don't really need the absolute values here because the 1 and the 5 are both positive. Is the lower limit going to give us any volume? What is the natural log of 1? 0. When you think about that log function, remember that y equals natural log of x looks like that. It goes right through 1. So the natural log of 1 is 0. Plug it in 1 here. So this is not going to contribute any volume. We're going to get pi multiplied by the natural log of 5. Don't need the absolute value bars because 5 is positive. I want to point out a feature that is going to become super important throughout the semester. You're going to see it a ton. When you look at this integral, what's the relationship between the denominator and the numerator? The denominator is what is the numerator? The denominator's derivative is the numerator. This is going to be a form that we are going to apply a name to. We are going to call it log form. Because every single solitary time that you have this, you end up with that. Every single solitary time. So we are going to call this log form. So if you have this situation, think about it for a moment. If you let u be the denominator, like we just said, then u's derivative would be f prime dx. So this will turn into the integral of 1 over u du. You'll get that. We'll do it a bunch. Just start thinking about that. Keep that in the hopper. All right, let's go to another shell. So this time, we take our region. We're going to rotate it around the x-axis. Rotate it around the x-axis. We're going to create this top-looking thing. And if you rotate that horizontal rectangle, you can kind of see the cylinder that you're going to get, that's going to be created. So that is parallel to the axis of rotation, so it creates a cylinder. We know that the area of a cylinder is 2 pi RH. Are we going to integrate with respect to x or with respect to y? How thick is that rectangle? dy. It's horizontal, so its thickness is dy, so we integrate with respect to y. Okay, so we know we're going to integrate with respect to y. That means when we replace our generic r and our generic h, they need to turn into expressions that have y's, not x's. Right? So if we're going to have a dy in the end, the r and the h have to be y's, cannot be x's. So let's start figuring this out. When we think about 2 pi r, so you're imagining this cylinder. Let's maybe even draw it in without letting it get too messy. That's not the best. So this is going to rotate and create that cylinder. Okay? What is the radius of that cylinder? That distance right there is the radius of the cylinder, right? What is that distance?
Y.
Y. Right? That's what the y on the y-axis is representing. That y right there is saying, ooh, this distance to the x-axis is y. Well, that's going to be the radius of the cylinder that you create if you take that horizontal line at y and you rotate it around. You're going to create a cylinder of radius y. So that is what goes here. Okay, now the height. The height's a little trickier. The height is sideways. The height is the length of that red segment. Horizontal, sideways. Back to basics. Horizontal distance, right x coordinate minus left x coordinate. So we need to know the coordinates. We need to know the x value at each of these places. Well, those x's are both coming from variables. There's no like vertical line so that the x is constant. So we have to be a little thoughtful here. So we've got, let's take a look at this function first. So that function is this one right here. That's y equals square root of x. But if we're measuring horizontal, we need to isolate x. We need it to be measuring horizontal distance, so we isolate x. So what is x going to equal? X will be, you saw, so we're going to square both sides. And then over here on this side, this curve is y equals 2 minus x. So it's measuring height. It's not measuring horizontal distance. To force it into the horizontal distance measuring model, we have to isolate x. So x will be equal to
Minus y plus
2 minus y. If you add the x to the left and subtract the y to the right, you'll end up with x equals 2 minus y. So now we have the left boundary written as an x value. We have the right boundary written as an x value. So the height is going to be right x, which is 2 minus y. That's the right x value, minus the left x value. The x value over here is y squared. So there is the area of the cylinder at height y. Area of the cylinder at height y. 2 pi RH. H is horizontal, so it's right x minus left x. We have to write each curve as an x value. So we isolate x in both curves. The volume we then find by integrating this. We'll distribute the y so that we have negative y cubed minus y squared plus 2y dy. The y values are going from 0, apparently up to 1. We should confirm that. If we want to know where these two curves meet, we have square root of x equals 2 minus x. Just to confirm, we could plug in the 1. We say, oh, yeah, well, if you plug in y equals 1 here, you get x equals 1. If you plug in, you see, you could do it by substitution. But the algebra way to do this would be to square both sides. And then solve for x. Although, technically, I actually want to be doing the y's equal to each other, because these are the two curves that we should be setting equal to each other. This will work, but let's actually do it with the ones that we generated. So we want to know, we're trying to find a y limit of integration. So if we set these two x's equal to each other, this will give us the y value. The other one will give us the x value, which we could then plug in and get the y value, but this will be more direct. Nonlinear equation, everything to one side and factor. That's our principle from algebra. This will be y plus 2 times y minus 1 equals 0. So y is equal to negative 2 or 1. We are in quadrant 1. So for our context, that's an extraneous solution. That tells us our y value where they intersect is at 1. And now to integrate this, we are going to use the power rule. So we will get our typical antiderivative when we have a polynomial, 0 to 1. And 0 is not going to give us anything. So we just need to know how to deal with fractions. So that'll be our volume. Just have to get a common denominator of 12. And that will be our volume. So if we multiply that one by 3 over 3, multiply that one by 4 over 4, multiply that one by 12 over 12, we will end up with 12 minus 7, which is 5. And then we'll cancel a 2 out of that and a 2 out of that. So 5 pi over 6. That will be our volume. All right, you ready to try one? They're a little tricky, but I think you're ready. All right, so go for it. So we want to find the volume of the solid generated by rotating that shape around the x-axis. And we're told that we are going to go, we're given that we're going to start at 1 over root 3 in the x direction here. And then we're going to stop at y equals 1 here. So y equals 1 and x equals 1 over root 3. Those are our two limits. If you want me to give you a nudge. Ask yourself, should it be dx or dy? remind yourself how you find horizontal distances and vertical distances? Should it be a dy or a dx? Is it clear to everyone what it should be? Dy or dx? Dy. It's always a dy. Dy? Yep. So it's a horizontal, so the thickness of that rectangle is a dy. Which tells you each piece of your cylinder formula needs to turn into y's. So I'm going to ask you one question about this. So this is the height of your cylinder, right? Is your height, is your cylinder height vertical or horizontal? Yeah, it's horizontal. So if it's horizontal, it should be, the right x minus the left x. That is the right x. That is right x. Horizontal distance for the height of your cylinder should be right x minus left x. I'm just going to put the h in here. So there's the height of your cylinder. And I see most of you are seeing that the radius is that distance. That's the radius, and that distance is given by y. Tell me what the left x is for that height. That's the right x. Yes.
I just didn't know how to put that in the form of y.
So it's already there, right?
This is-
This is written as x equals blah blah. This is also, because this is a constant, x equals 1 over root 3, so it's already got x isolated. So
Oh, we didn't have to isolate y.
no, because it's a horizontal distance, you're going to do the right x value. So the x value is whatever's to the right of the equal sign. That's the x value on the right. And the x value on the left is x equals 1 over root 3. This guy here, this is your right x value, that thing. Minus your left x value is this guy. Right, because that vertical line right there is what's on the left, that's that rectangle. So that's your left, and that's your right.
So this should be
We should leave it as x, because we are finding horizontal distance, which means we want to isolate x, and x is already isolated there for us. And that's already isolated. Yeah, exactly, that one. Yep. Seeing it?
No, honestly, I'm just dead on my feet. I don't I can't think at the moment.
Yeah, that is.
This is inactive.
Oh, that's not our.
No, I've had like 3 hours of sleep and I've been awake for 8. Yes.
What time do you?
I go to work at 1:20 in the morning and I get off at 8:50.
Oh gosh, you get off at 8:50?
Yes.
And then comes right here. Sounds like
keep me nodding off. I'm not trying to be mean, but
So that sounds like you need some recovery. Coming to calculus to recover from your night shift.
and then I'm here until 3:45.
Sadist.
On the other hand, my work's paying for this, so
Right.
I'll accept it.
Right. You'll pay for the suffering. You'll endure the suffering. All right, so let's try to go through this slowly. It's like a big puzzle. It's like a jigsaw puzzle. We have to ask ourselves lots of little questions. The first thing is making sure you know whether it's going to be a dy or a dx. If you know it's going to be a dy or a dx, that leads you down a road that's helpful. If you don't know whether it should be a dy or a dx, then it's kind of hard to dig in right away. And so we want to have our basic principle that the thickness of a horizontal rectangle is dy, the thickness of a vertical rectangle is dx. So as soon as we see that that thickness is dy, we know that in our generic formula for a cylinder, which is 2 pi rh, we know that these two generics have to be replaced with expressions that have a y in them. Because eventually we have to integrate the area with respect to y. So we know that both those have to be turned into expressions with just y, no x's. So now we visualize this segment rotating around the x-axis to create the cylinder that it's going to create. Okay? The distance that this element is, this rectangle, the distance it is down to the axis of rotation is given by that right there, y. Right? So this y coordinate is somewhere between 1 and square root of 3. It's variable though, right? So if it happens to be right there, then the y value will be that. If it happens to be down here, the y value is 1. But it's a variable. It's generic. It's general. I don't want to say generic. General. So the radius is y. That is what that y is going to represent. So, and we're on the right track, right? We know we have a dy, so we should have just y's up here. So we constantly are making this check in our head. dy is our baseline. And we know we need to have y's in here because we're going to integrate this with respect to y. Now the harder one. The harder one is the h. We need to know what this h is. And go back to the basics again. We look at that h, it's horizontal. Anytime we have horizontal distance, it's the right x value minus the left x value. So if we're sitting there on the x-axis and we're here at 10 and we're at -1, 10 minus minus 1 is 11. That is the distance. Here we have variables. Things are changing. So the x value on the left, though, is constant. Right? This curve, right here, this curve, which is a line, right? Line is a curve, that is x equals 1 divided by root 3. That is the left x value. It's that vertical line. The right x value is that curve, and they did give it to us as an x value. So it doesn't need to be rewritten. Horizontal distance, x minus x. This is the value. The value is what's right on the other side of the equal sign. When we say x equals 1 over root 3, the value of x is 1 over root 3. Over here, the value is variable. The value is 4 divided by y plus y cubed. So that'll be all plugged in here. The right x value minus the left x value. So that is our generic area. or a general area. Oh my gosh, what time does this class end?
45.
In 45 seconds or something? Like rapidly? All right, well, let's just set up our volume here. Time is flying. So I'm going to distribute this y so that we have 4y over y. Oh, it's going to end up canceling here. And distribute the y over here. And that will be dy. How about the y limits? Can you see those from the graph? So it's horizontal, so that means the domain is over here. So 1 over this 1, y equals 1 to y equals square root of 3. So there's our setup. So we'll go through the evaluation of that integral on Thursday. Office hours right now, I'll stay in here until 12:30 for anyone that wants to enjoy a little more math. 2 hours and 15 minutes isn't enough? Or maybe, did you have anything today? Okay, good. So if you've already done 3 hours and 15 minutes of math and you want to do more, come to the right place. If not, I'll see you on Thursday.
See ya.
Thank you. Absolutely.
Homework start due tonight?
No, tomorrow night. Homeworks are always due on Wednesday nights. So Wednesday nights.
It's Tuesday.
Yeah, today is Tuesday. So tomorrow night is our first homework due. 6-1, 6-2, and 6-3 tomorrow night.
Thank you.
Oh yeah, thank you so much.
Yeah.
All right. Let me hit stop on this guy real quick.